Principles of Bioproduct Separation, Module 9, Elution Chromatography, Segment 3, Discrete Stage Analysis. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. We have previously discussed about absorbance and yield and purity. In this segment, we will discuss about discrete stage analysis. This analysis assumes that the chromatographic column is not a continuous packed bed, but a series of stages, like shown in the right figure. Each stage is like a well-mixed tank of fixed volume in which the solution and adsorbent are in equilibrium. Solvent flows from one stage to the next, but adsorbent remains within the same stage where it begins. We can use this model for chromatography by writing solid mass balance on each stage, as shown in equation 13 and equation 14. Solid concentrations in the solvent and the adsorbent are assumed to be in equilibrium, which can be expressed as shown in equation 15, which is a linear isotherm. Combining equation 14 and equation 15 yield equation 16, which is a key equation that must be solved for all stages in the column. Originally, none of the stages contain solute. Initially, we do inject into the column the contents of a feed stage. Concentration in each stage can be calculated using equation 17, which has a Poisson distribution. The stage volume Vs can be replaced with a bed volume, which results to equation 19. Concentration profile of the solute is as shown in the figure. When the number of stages is small, the distribution looks like a decaying exponential. However, as the number of stages becomes large, the profile approaches the Gaussian limit, which can be expressed by equation 20. In a Gaussian distribution, the concentration Y is given as a function of three variables, tau null, sigma, and Y null. The first parameter, tau null, the mean dimensionless time in which the solid leaves the column, can be calculated by using equation 21 and equation 22. The second parameter, sigma, can be obtained from equation 23. The third parameter, Y null, depends on a mass balance over the whole chromatographic column, and the point derivation can be calculated using equation number 24. The dimensionless time in equation 24 can be replaced with an actual time t, which can be expressed by equation 25, where t null is the actual time in which the peak exists, which can be calculated using equation 26. Hence, the concentration profile in terms of time and volume eluted can be calculated using equation 27 and equation 28. We can use an experimentally measured concentration profile to determine number of stages. For the next segment, we will discuss about kinetic analysis. Until then, I am Yusuf from Institut Teknologi Bandung.